Hello everybody, welcome into another lesson. So today we are going to start part 1 of 2 of verifying trig identities. Today we're going to focus heavily on algebraic trig identities. In the next lesson we'll focus on other types. But for today we're going to verify some algebraic identities. And for the first one here you have the sine of 1/2 x cosine of x minus sine 5/2 of x cosine of x equals the cosine cubed of x square root sine of x. Okay, so if we remember, whenever verifying an identity, write out the left hand side again. So that's going to be the sine of 1/2 x cosine of x minus the sine of 5/2 x cosine of x. Now, we definitely want to factor out common terms. That's definitely going to be sine of 1/2 x times the cosine of x. So you factor out a common sine of 1/2 x cosine of x. What you would be left with is going to be 1 minus sine squared of x. That's what you would have left once you factor. Well, what's 1 minus sine squared of x? That's cosine squared of x. So you would end up with sine 1/2 of x times the cosine of x times the cosine squared of x. Well, cosine times cosine squared, that's cosine cubed. So this would turn into cosine cubed of x. Sine of 1/2 x is the same as the square root of the sine of x. So we just got what we desired to achieve. So therefore, we can say that the sine of 1/2 x cosine of x minus the sine of 5/2 x cosine of x equals the cosine cubed of x times the square root of the sine of x. I must have got a bad marker or something. It's definitely not writing the best, and that was a brand new marker. Okay, that was weird. Anyway, so there's that one. I got more. Alright, so we have another one here. We have secant 6 of x times secant x tangent of x minus secant 4 of x times secant x tangent of x is equal to secant 5 of x tangent 3 of x. Alright. So we have secant 6 of x times secant of x tangent of x. I keep forgetting to write that x. Minus secant 4 of x secant of x tangent of x equals secant 5 of x tangent cubed of x. Well, let's write out the left-hand side again. So secant 6 of x times the quantity of the secant of x tangent of x minus the secant 4 of x times the secant of x tangent of x. Let's factor. So you're definitely going to have to factor out some common terms. You can start with the secant 4 of x. So this would turn into the secant 4 of x, but what else do you have in common? You have a common secant of x tangent of x. You can also factor that out. And then what are you left with once you factor those? You're left with a secant squared minus 1. So you're left with a secant squared of x minus 1. Now, what is secant squared of x minus 1? That just turns into tangent squared of x. So this would turn into the secant 4 of x times the quantity of the secant of x tangent of x times the tangent squared of x, which when simplified will give you secant 5 of x tangent 3 of x. So we've just achieved our desired result, so therefore we can say the secant 6 of x times the quantity of the secant of x tangent of x minus secant 4 of x times the quantity of secant of x tangent of x equals secant 5 of x tangent 3 of x. So yeah, that one was a little bit of a long identity, but that's exactly how you'd verify it, using your Pythagorean identities and factoring. Excuse me. Now, what if we had something like the cotangent of the quantity of pi over 2 minus x times the cosecant of x equals the secant of x. So we need to verify that the cotangent of pi over 2 minus x times the cosecant of x equals the secant of x. Well, we notice that cotangent one is a periodic identity. So let's write out the left-hand side first. The cotangent of the quantity of pi over 2 minus x times the cosecant of x. Again, this is a periodic identity, which would turn this into the tangent of x. So this would turn into the tangent of x times the cosecant of x. Now we just need to use our reciprocal identities. So what's the tangent? That's the sine of x over the cosine of x times your cosecant. That's 1 over sine of x. Well, your sines cancel out. You'd be left with 1 over the cosine of x, which we know to be the secant of x. So therefore, the cotangent of pi over 2 minus x times the cosecant of x equals the secant of x. Alright, so next one we have here is the secant of pi over 2 minus x divided by the tangent of pi over 2 minus x is equal to the secant of x. So we have to verify that the secant of the quantity of pi over 2 minus x divided by the tangent of the quantity of pi over 2 minus x is equal to the secant of x. So let's write out that left-hand side here real quick. Secant of pi over 2 minus x all over the tangent of pi over 2 minus x. Okay. Now, we can simplify both the numerator and denominator because they are periodic identities. That secant would actually turn into a cosecant due to the periodic identity. So we'll have cosecant of x divided by that tangent of pi over 2 minus x is periodic for the cotangent of x. So this would turn into cosecant of x over cotangent of x. Now in both numerator and denominator, we need to use our reciprocal identities. Cosecant is 1 over sine of x divided by your cotangent, which is going to be cosine of x over the sine of x. And since you have a complex fraction, you're just going to invert and multiply. So this would turn into 1 over the sine of x times the sine of x over the cosine of x. Well, your sines will cancel out. This would simplify into 1 over the cosine of x, which we know to be the secant of x. So we've just verified this identity. So therefore, the secant of the quantity of pi over 2 minus x divided by the tangent of the quantity of pi over 2 minus x is equal to the secant of x. All right. So we have the cosecant of negative x all over the secant of negative x. We are being asked to verify that that equals the negative cotangent of x. Alright, so let's write out the left-hand side again. So we have the cosecant of negative x all over the secant of negative x. Well, we definitely have some even and odd identities to start with. Cosecant's an odd function, so that would just turn into negative of the cosecant of x all over your secant of negative x. Secant's even, cosecant's odd, but secant's even, so this would just be the secant of positive x. Well, now it's time to use some reciprocal identities in the numerator and denominator. So what is the cosecant? That's 1 over sine. In this case, this would be negative 1 over the sine of x divided by your secant. Well, secant is 1 over cosine of x, which, since you have a complex fraction, you'll invert and multiply, so you'll have negative 1 over the sine of x times the cosine of x, which would just turn into the negative cotangent of x. So we've just verified the identity. So therefore, the cosecant of negative x over the secant of negative x equals negative of the cotangent of x. Alright, so we have 1 plus sine of y, that quantity times the quantity of 1 plus the sine of negative y is equal to the cosine squared of y. We have to verify that. So let's write out the left-hand side again. You'll have 1 plus the sine of y times the quantity of 1 plus the sine of negative y. Well, in your second quantity, we have an even-odd identity. The sine of negative y, since sine's an odd function, this would actually turn into the quantity of 1 plus sine of y times 1 minus sine of y. Well, now you just got a FOIL. You should end up getting 1 minus sine squared of y, which is going to be cosine squared of y. So now we have verified the identity. So therefore, 1 plus sine of y times the quantity of 1 plus the sine of negative y equals the cosine squared of y. All right. So now let's see, the cosine of negative theta all over 1 plus the sine of negative theta, we have to verify that that is equal to the secant of theta plus the tangent of theta. So let's write out the left-hand side again. So the cosine of negative theta all over 1 plus the sine of negative theta. All right, so to start with, we have some even and odd identities. Cosine is even, so that would just become the cosine of positive theta all over your denominator. Well, sine's an odd function, so this would turn into 1 minus the sine of theta. Now, of course, we don't want to have a difference or a sum in the denominator, so we need to rationalize the denominator by multiplying by its conjugate. So this would be times 1 plus the sine of theta all over 1 plus the sine of theta. All right, so now in the numerator you'll have the cosine of theta times the quantity of 1 plus the sine of theta all over 1 minus sine squared of theta. Well, 1 minus sine squared, that just becomes cosine squared. So this would be cosine of theta times 1 plus the sine of theta all over the cosine squared of theta. Well, you have a cosine that'll cancel out between numerator and denominator, so now you have 1 plus the sine of theta all over the cosine of theta. Well, we could separate these terms. What's 1 over cosine? That's secant, so this would turn into the secant of theta plus sine of theta over cosine of theta. That's tangent of theta. So we have achieved our desired result, so we have verified the identity. So therefore, the cosine of negative theta all over 1 plus the sine of negative theta is equal to the secant of theta plus the tangent of theta. All right. We just did that one. Let's do this one. So we have 1 plus the cosecant of negative theta all over the cosine of negative theta plus the cotangent of negative theta is equal to the secant of theta. So we have to verify that 1 plus the cosecant of negative theta all over the cosine of negative theta plus the cotangent of negative theta equals the secant of theta. Well, let's write out our left-hand side again. So 1 plus the cosecant of negative theta all over the cosine of negative theta plus the cotangent of negative theta. All right, so we have some even and odd identities. Cosecant's an odd function, so the numerator would turn into 1 minus the cosecant of theta all over your denominator. Cosine's an even function, so that would just be the cosine of positive theta. And then the cotangent function is odd, so this would be minus the cotangent of theta. All right, so next we need to do some reciprocal identities in the numerator and denominator. So this would turn into 1 minus 1 over the sine of theta all over the cosine of theta minus the cosine of theta all over the sine of theta. Well, we definitely in the numerator and denominator have to get the same common denominator, which is in both cases will be the sine of theta. So this would turn into the sine of theta minus 1 all over the sine of theta all over the sine of theta cosine of theta minus the cosine of theta all over the sine of theta. Now you have a complex fraction, so you just have to invert and multiply. So this will turn into the sine of theta minus 1 over the sine of theta times the sine of theta all over the numerator of the denominator. You can factor out a common cosine of theta times the sine of theta minus 1. Well, you end up canceling out your sines of theta. You also end up canceling out the sines of theta minus 1. You end up with 1 over the cosine of theta, otherwise known as the secant of theta. So we have just verified this, that 1 plus the cosecant of negative theta all over the cosine of negative theta plus the cotangent of negative theta equals the secant of theta. So yeah, that one was a bit messy. All right. So these ones used a lot of reciprocal and periodic and even some Pythagorean identities. Now, we got some ones coming up that are going to have some radicals in them. But first we got some fractions. So we have the cosine of x minus the cosine of y all over the sine of x plus the sine of y plus the sine of x minus the sine of y all over cosine of x plus the cosine of y. We have to verify that that all equals 0. Well, we definitely want to get the same common denominator for both of these terms, so let's write this out here. Cosine of x minus cosine of y all over the sine of x plus the sine of y plus the sine of x minus the sine of y all over the cosine of x plus the cosine of y. Well, basically now you're just going to have to take the first term, multiply it by this denominator, and FOIL. You should end up with cosine squared of x minus cosine squared of y. And then take this and FOIL with this, so you would end up with plus the sine squared of x minus the sine squared of y all over these two denominators multiplied together. So the sine of x plus the sine of y times the cosine of x plus the cosine of y. Alright, well, let's look at something here. You can group your x terms together, so you'll end up having the cosine squared of x plus the sine squared of x. And then both your cosines and sines of y are negative, so you can factor out a -1. This would be minus the cosine squared of y plus the sine squared of y all over the quantity of the sine of x plus the sine of y times the quantity of the cosine of x plus the cosine of y. Well, what are each of these cosine plus sine squareds? That's going to equal 1 minus 1 all over the quantity of the sine of x plus the sine of y times the cosine of x plus the cosine of y, which I think it's fairly obvious that 1 minus 1 is 0, therefore giving you 0. So therefore, the cosine of x minus the cosine of y all over the sine of x plus the sine of y plus the sine of x minus the sine of y all over the cosine of x plus the cosine of y is equal to 0. That one was a bit of a doozy, but that's exactly how it worked out. All right, let's see. We have the tangent of x plus the cotangent of y all over the tangent of x cotangent of y is equal to tangent of y plus the cotangent of x. So what a twist that was. Well, let's write out the left-hand side. So this would end up being tangent of x plus cotangent of y all over the tangent of x times the cotangent of y. This one is not as bad as it looks. If you separate these into two separate terms, in the first term the tangent of x would cancel out. You would be left with 1 over the cotangent of y plus, let's look at the second term, cotangent of y over tangent of x cotangent of y. Well, your cotangents of y would cancel out, so this would be 1 over cotangent of y plus 1 over the tangent of x. And 1 over cotangent of y is simply the tangent of y, plus 1 over tangent of x, that's the cotangent of x. So that one actually wasn't that bad. So therefore, the tangent of x plus the cotangent of y all over the tangent of x cotangent of y equals the tangent of y plus the cotangent of x. So that one actually was not that bad. Alright, we have a couple of radical ones. We have to verify that the radical of 1 plus the sine of theta all over 1 minus the sine of theta, the square root of that whole expression, is equal to 1 plus the sine of theta all over the absolute value of the cosine of theta. And at the end, I'll go over why we have an absolute value for the cosine. But let's start here. So if we write out the left-hand side, 1 plus the sine of theta all over 1 minus the sine of theta, okay? Well, I deliberately left some extra room under the radical, actually. Before we even try to figure out this radical business, we need to rationalize the denominator inside the radical. So you multiply both numerator and denominator by the conjugate of the denominator, which would be 1 plus the sine of theta in both cases. Well, this would turn into the square root of 1 plus the sine of theta, that quantity squared, all over 1 minus sine squared of theta. Well, what is 1 minus sine squared of theta? That's going to end up being the square root of 1 plus the sine of theta, that quantity squared, all over the cosine squared of theta, which both will break down nicely into simply 1 plus the sine of theta all over the absolute value of the cosine of theta. And the reason that cosine has an absolute value symbol is because you don't want to have a negative value of theta inside your square root and possibly end up risking getting an undefined value. And the reason sine doesn't have the absolute value is because no matter what value you put in for sine, the lowest value you're going to get is 0. So 0 is defined. And if you did negative 1, and even if you did 1 in the denominator, well, that would be undefined, but that's a whole other story. The idea is that if it's a single expression of trig that doesn't have anything added to it, it's usually an absolute value. So we can say that therefore the square root of 1 plus the sine of theta all over 1 minus the sine of theta is equal to 1 plus the sine of theta over the absolute value of the cosine of theta. And I got more of these. Alright, let's see. We have the square root of 1 minus the cosine of theta all over 1 plus the cosine of theta. We are being asked to verify that that is equal to 1 minus the cosine of theta all over the absolute value of the sine of theta. So let's start with the left side again here. So 1 minus the cosine of theta all over 1 plus the cosine of theta. Alright, so before we even deal with that radical business, we need to rationalize the denominator. So multiply by the conjugate times 1 minus the cosine of theta all over 1 minus the cosine of theta. Well, this will turn into the square root of the quantity of 1 minus the cosine of theta raised to the second power all over 1 minus cosine squared of theta. Well, what's 1 minus cosine squared? That's sine squared. So this would turn into the square root of the quantity of 1 minus the cosine of theta quantity squared over sine squared of theta, which both of these are perfect squares, so this would turn into 1 minus the cosine of theta all over the absolute value of the sine of theta. So, therefore, we can say that the square root of 1 minus the cosine of theta all over 1 plus the cosine of theta equals 1 minus the cosine of theta all over the absolute value of the sine of theta. All right. Let's see, we have the sine squared of the quantity of pi over 2 minus x plus the sine squared of x equals 1. So we have to verify that sine squared of the quantity of pi over 2 minus x plus sine squared of x equals 1. This won't be bad at all. Let's write out the left-hand side first. Sine squared of pi over 2 minus x plus the sine squared of x. Okay, well, we definitely have in our first term a periodic identity. This would actually turn into the cosine squared of x plus the sine squared of x, which we know is just 1. So therefore, the sine squared of pi over 2 minus x plus the sine squared of x equals 1. That one was not so bad. All right. Let's see, we have the secant squared of y minus the cotangent squared of pi over 2 minus y equals 1. So we have to verify that the secant squared of y minus the cotangent squared of pi over 2 minus y equals 1. So let's write out the left-hand side, and this one's not going to be that bad either. So secant squared of y minus cotangent squared of pi over 2 minus y. Well, we have another periodic identity on the cotangent. That would just turn into the tangent of y. So this would turn into the secant squared of y minus the tangent squared of y, which is better known as 1. So therefore, the secant squared of y minus the cotangent squared of the quantity of pi over 2 minus y is equal to 1. All right, let's see. We have to do sine of x times the cosecant of pi over 2 minus x equals the tangent of x. All right, so we have to prove that the sine of x times the cosecant of pi over 2 minus x equals the tangent of x. So let's write out that left-hand side again. So sine of x times the cosecant of pi over 2 minus x. All right, so the cosecant's a periodic identity. This would actually turn into the sine of x times the secant of x, which now with the secant we can use a reciprocal identity. This would turn into the sine of x times 1 over cosine of x, which would give you the tangent of x. So therefore, the sine of x times the cosecant of pi over 2 minus x equals the tangent of x. All right, let's see. One more of these, then we're going to get into true polynomial types here in just a minute. So let's see. We have the secant squared of the quantity of pi over 2 minus x minus 1 equals the cotangent squared of x. So let's write out the left-hand side again. You have the secant squared of pi over 2 minus x minus 1. Okay, so that's a periodic identity on the secant, so this would actually turn into cosecant. So this would be the same thing as the cosecant squared of x minus 1. Well, we know 1 plus cotangent squared equals cosecant, so that means cosecant squared minus 1 equals the cotangent squared. So we just proved that identity, so therefore the secant squared of pi over 2 minus x minus 1 equals the cotangent squared of x. Alright, for the last phase of the lesson, let's get into some true polynomial types. So, we are going to have 2 secant squared of x minus 2 secant squared of x sine squared of x minus sine squared of x minus cosine squared of x equals 1. So that's a rather long one. That one was rather long, so I do apologize in advance, but let's see here. So 2 secant squared of x minus 2 secant squared of x sine squared of x minus sine squared of x minus cosine squared of x equals 1. Well, let's start with factoring by grouping here. So the first two terms, you definitely have 2 times the secant squared of x in common. So this would be 2 secant squared of x times 1 minus the sine squared of x minus, now we can factor out a negative 1 from the last two terms and get the cosine squared of x plus sine squared of x. Well, what do we have now? You have here, for the first term, 1 minus sine squared, that's cosine squared. So you would have 2 secant squared of x cosine squared of x simply minus 1, because the cosine squared of x plus sine squared of x equals 1. Alright, well, what's secant? That's 1 over cosine, so you would end up having 2 over the cosine squared of x times the cosine squared of x, all that minus 1, which your cosine squareds will cancel out. This will just give you 2 minus 1, which equals 1. So therefore, 2 secant squared of x minus 2 secant squared of x sine squared of x minus sine squared of x minus the cosine squared of x is equal to 1. All right. So we have cosecant of x times the quantity of the cosecant of x minus sine of x plus the sine of x minus the cosine of x all over the sine of x plus the cotangent of x is equal to cosecant squared of x. This one looks particularly nasty, and it kind of is. So let's write out the left-hand side again. I'm going to start all the way at the left so we don't run out of space. Cosecant of x times the quantity of cosecant of x minus the sine of x plus the quantity of the sine of x minus the cosine of x all over the sine of x plus the cotangent of x. So what the heck does that equal? Well, let's distribute first. Cosecant times cosecant, that's cosecant squared of x minus, now cosecant and sine are reciprocal, so that would just be minus 1, plus then you'll have the sine of x minus the cosine of x all over the sine of x plus what is your cotangent of x? That's actually the cosine of x over the sine of x. So what's that going to equal? All right, cosecant squared minus 1. Well, it's important to know that cosecant squared minus 1 is cotangent squared. So this would turn into cotangent squared of x plus that sine of x minus the cosine of x all over the sine of x plus the cosine of x all over the sine of x. Well, cotangent squared is what? That's going to be cosine squared over sine squared. Cosine squared of x over sine squared of x. So that means our common denominator should actually be sine squared. So we have to multiply all these other terms by sine in order to get that. So this would be plus sine squared of x minus sine of x cosine of x plus sine of x cosine of x. All this is going to all be all over sine squared. This simplifies quite nicely. What's cosine squared plus sine squared? That's just 1, and then these two cancel out since they go to 0. So you would end up getting 1 over the sine squared of x, which would simplify into the cosecant squared of x. And I think you all get it with the therefore statements. Make sure you write therefore the left side equals the right. That's all you really have to do. But we verified that one quite nicely. Alright, so we have the cotangent of x times the tangent of x all over the sine of x equals the cosecant of x. This one ain't going to be nothing because let's write out that left-hand side. We have the cotangent of x times the tangent of x all over the sine of x. Okay, so what is cotangent? That's simply 1 over tangent, right? This would be the same as 1 over tangent of x times the tangent of x. All that all over the sine of x. Well, your tangents would cancel out. You would just get 1 over the sine of x, which would give you the cosecant of x. So don't forget to write your therefore statement once you're done. But that one worked out quite nicely. All right, let's see. 1 plus cosecant of theta all over secant of theta minus the cotangent of theta equals the cosine of theta. This one looks a bit rough. Well, we should definitely, well, first let's write out that left-hand side and simplify it. So 1 plus the cosecant of theta all over the secant of theta minus the cotangent of theta. All right, so all these basically are reciprocal identities. So the cosecant of theta, so this would turn into 1 plus 1 over the sine of theta all over your secant of theta, which is going to end up being 1 over the cosine of theta, minus, now what's the cotangent? That's cosine of theta over the sine of theta. Okay, so in the numerator, we definitely want to get a common denominator. That would be the sine of theta. So in the end, you should have the sine of theta plus 1 over the sine of theta all over 1 over the cosine of theta minus the cosine of theta sine of theta. Well, you have a complex fraction on your first term, so just invert and multiply. You'll have the sine of theta plus 1 all over the sine of theta times the cosine of theta minus the cosine of theta over the sine of theta. All right, so let's see what you get here. So when you simplify this out, these actually all have the same denominator. You're going to end up getting sine of theta cosine of theta plus the cosine of theta minus the cosine of theta all over the sine of theta. Well, cosine minus cosine cancels out. You'll end up getting the sine of theta cosine of theta all over the sine of theta. Well, the sines cancel out between numerator and denominator. You're just left with the cosine of theta. So that one did in fact simplify down to the cosine of theta. Let's see, I have about 1, 2, 3, 4, 5, 6, 7, 8 more. So we have here that the cosecant 4 of x minus 2 cosecant squared of x plus 1 is going to be equal to the cotangent 4 of x. So we have to verify cosecant 4 of x minus 2 cosecant square of x plus 1 equals cotangent 4 of x. Okay. Well, this is definitely a difference of squares on the left-hand side. So this is going to be the cosecant 4 of x minus 2 cosecant squared of x plus 1, that's actually going to be that the cosecant squared of x minus 1 squared. Well, what's cosecant squared minus 1? That's cotangent squared, so you would end up having the cotangent squared of x squared, which would be the cotangent to the fourth of x. And don't forget to write your therefore statement at the end, but that one actually simplified quite nicely. Alright, so we have the sine of x times the quantity of 1 minus 2 cosine squared of x plus cosine to the fourth of x all equals sine 5 of x. This one's not going to be as bad as you think. Let's write out the left side again. So we have the sine of x times the quantity of 1 minus 2 cosine squared of x plus cosine 4 of x. Okay, well, what's true about the parentheses? That's another that's another binomial square. So this would actually turn into the sine of x times the quantity of 1 minus cosine squared of x, quantity squared. Okay, so what's 1 minus cosine squared of x? That's the sine of x. So this would turn into the sine of x times the sine squared of x squared. Well, what's sine squared squared? That's sine to the fourth, so you would have sine of x times sine 4 of x, which would simplify into sine 5 of x. And don't forget to write your therefore statement, and you have that answer. And these are perfect to know when you're doing integration in Calc 2. These will definitely help you to be able to solve those. Alright, let's see. Secant 4 of theta minus tangent 4 of theta is equal to 1 plus 2 tangent squared of theta. Alright, so we definitely have a difference of 2 squares on the left-hand side. So this will end up being secant 4 of theta minus tangent 4 of theta. Well, this is going to break down into the secant squared of theta minus the tangent squared of theta times the quantity of the secant squared of theta plus the tangent squared of theta. Alright, so what's secant squared minus tangent squared? That's actually just 1, so you'll end up with secant squared of theta plus tangent squared of theta. Alright, well, we're supposed to get this in terms of 1 plus 2 tangent squared of theta. So what is secant squared? That's just 1 plus tangent squared, right? So we can take 1 plus tangent squared of theta plus that tangent squared of theta. You actually end up getting it's equal to 1 plus 2 tangent squared of theta. And don't forget to write your therefore statement, and then you're done. Five more. Alright, so we have the cosecant 4 of theta minus cotangent 4 of theta, we're being asked to verify that it equals 2 cosecant squared of theta minus 1. So let's write out that left-hand side again. So cosecant 4 of theta minus cotangent 4 of theta. Well, that's a difference of 2 squares. This would turn into the quantity of the cosecant squared of theta minus the cotangent squared of theta times the quantity of the cosecant squared of theta plus the cotangent squared of theta. Well, what's cosecant squared minus cotangent squared? That's just 1, so now you're down to cosecant squared of theta plus the cotangent squared of theta. Well, what's another way of writing cotangent squared so we can get 2 secant squared minus 1? Cotangent would actually be cosecant squared minus 1. So you could put in cosecant squared of theta, then for that cotangent squared, put in plus cosecant squared of theta minus 1, which would simplify into 2 cosecant squared of theta minus 1. And don't forget to write your therefore statement, and that's it. 4 more, then we're done. All right. So let's see. We have to prove that the sine of beta over 1 minus the cosine of beta is equal to 1 plus the cosine of beta all over the sine of beta. So let's write out the left-hand side again. This is going to involve more rationalizing. So we're going to rationalize the denominator, so we'll take both numerator and denominator times 1 plus the cosine of beta all over 1 plus the cosine of beta. Well, in the numerator, you'll end up getting the sine of beta times 1 plus the cosine of beta all over 1 minus cosine squared of beta. Well, what's 1 minus cosine squared? That's sine squared. So you would end up getting the sine of beta times 1 plus the cosine of beta all over the sine squared of beta. Well, a beta would factor out between the numerator and denominator for a final answer of 1 plus the cosine of beta all over the sine of beta. So we just verified the identity, and don't forget to write your therefore statement. And I got 3 more. Alright, so we have the cotangent of alpha all over the cosecant of alpha minus 1 is equal to the cosecant of alpha plus 1 all over the cotangent of alpha. So let's write out the left-hand side again. So this would end up being the cotangent of alpha all over the cosecant of alpha minus 1. Well, we actually shouldn't need any reciprocal identities. All we should need to do is rationalize the denominator. So take both numerator and denominator times the cosecant of alpha plus 1. Which in the numerator would turn into the cotangent of alpha times the quantity of the cosecant of alpha plus 1. all over your denominator ends up turning into cosecant squared of alpha minus 1. Well, that denominator would just turn into cotangent squared of alpha. So you'd end up getting cotangent of alpha times cosecant of alpha plus 1 all over cotangent squared of alpha, which a common cotangent will factor out. You end up left with cosecant of alpha plus 1 all over the cotangent of alpha. And write your therefore statement, and you got it. Got two more, then we're done. All right, so we have to verify that the tangent cubed of alpha minus 1 all over the tangent alpha minus 1 is equal to the tangent squared of alpha plus the tangent of alpha plus 1. That's actually not going to be hard at all. So let's write out the left-hand side again. So you have the tangent cubed of alpha minus 1 over the tangent of alpha minus 1. Now it's probably been a minute since you factored cubes. How do we do that? Well, take the cube root of both terms, so this would end up being the quantity of the tangent of alpha minus 1. Now, once you have that factor, square your first term, which would be tangent squared of alpha, and then multiply the two terms and negate it, so that would be plus the tangent of alpha, then plus your second term squared, so that would be plus 1. You'll have all that all over the tangent of alpha minus 1. And what do you know? The tangents of alpha minus 1 cancel out. You're just left with the tangent squared of alpha plus the tangent of alpha plus 1. And don't forget to write your therefore statement, and you're done. And I got one more similar one to this. Alright, so let's see. We have the sine cubed of beta minus the cosine cubed of beta all over the sine of beta minus the cosine of beta is equal to, no wait, that's plus on both, excuse me. So sine cubed of beta plus cosine cubed of beta over sine of beta plus cosine of beta equals 1 minus the sine of beta cosine of beta. All right, this one won't be so bad either. So write out your left-hand side. So the sine cubed of beta plus the cosine cubed of beta all over the sine of beta plus the cosine of beta. Okay, well, again, we're factoring cubes. So in the numerator, take the cube root of both terms, you'll get the quantity of sine of beta plus cosine of beta. Now take your first term and square it. You'll end up getting sine squared of beta. Now take your two terms, multiply them, then negate them. So you'll end up getting minus the sine of beta cosine of beta. Then square your second term. That'll be plus the cosine squared of beta. All that all over the sine of beta plus the cosine of beta. Well, at the very least, to start with, your sine of beta and cosine of beta terms cancel out. You're just left with sine squared of beta plus cosine squared of beta minus sine of beta cosine of beta. Well, what is sine squared plus cosine squared? That's just 1. So this will leave you with 1 minus the sine of beta, cosine of beta. Don't forget to write your therefore statement, and you're done. So that's it for this lesson. Next lesson, we're actually going to get into some logarithmic trig identities, verifying those. We're going to use periodic identities to solve some very simple trig equations. Then what else? We're also going to do some deeper factorization that's going to set us up for calculus, and then we'll even do some inverse trig identities. So I hope everyone has a great day. Take care.